Hello, this is the video for the chemistry content for Wednesday, May 5th. I know many of us didn't talk much about chemistry in class because we were taking a quiz and we were going over some multiple choice questions. So the intent of this video is to go over the first 5 of the organic reactions as found on your lavender types of organic reactions card. I'll be giving you notes that you should be putting into your class packet for organic reactions. I'll go at a moderate rate. You can stop at any time to write down these notes, but otherwise, I hope that my explanations will help you understand the content all the more. As I said, I'll do videos every day for the next 5 days, Wednesday, Thursday, Friday, and next Monday and Tuesday. There'll be a video for you to watch, and then you'll continue with your class notes and your homework packet as if we were having class together. The quiz will still be on Monday. So, to share my screen. So today I'm going to be looking at combustion, alkane substitution, addition, addition polymerization, and oxidation of alcohols. All right. I've already done this with one of the 2 classes, but not with period 4 or 5. Organic reactions primarily have to do about combustion. All organic compounds combust. If you look on your class notes, you'll see that in the description it says all organic compounds combust. Please make sure you read this description over on the right-hand side of your notes very carefully. That includes essential content for you to know. I give you that as a tip. So all organic compounds combust, either completely or incompletely, depending on the amount of oxygen available. Complete combustion will yield only carbon dioxide and water as products, but should you have an insufficient amount of oxygen, then you would have some carbon, carbon monoxide, and carbon dioxide and water as your products. So I fully expect you to be able to write and balance these chemical reactions. I know when we write propane, we normally write it out as a structural compound. But when you balance an organic reaction, I highly recommend that you write the formula in this molecular form. Now for propanol, I would never represent propanol, C3H8O, if I'm talking about the specific molecule of propanol, because this molecular formula is not specific enough to say this is 1-propanol. But it is easier to balance the equation if you write propanol like this. You can just keep track of the C's, H's, and O's a little bit easier. I emphasize these are not balanced. You should make sure that you're comfortable being able to balance the complete combustion of these representative organic compounds. You should do that. Check it with a friend. You can Google your answer, but this is a required skill. Next, alkane substitution. I emphasize that there are going to be 3 kinds of substitution reactions on this list of organic reactions. Alkane substitution specifically has to do with only alkanes. I made a point of saying alkanes are not very reactive. Alkanes do combust, but they don't do very much else as far as chemical reactivity. However, alkanes can be made with a lot of conditions to very slowly undergo a substitution reaction. Substitution means you take one atom off and put a different atom on. And here I point out to you that we are taking one of the hydrogens off, and we are going to be putting on one of these chlorines, such that you get 2 products. You get the chloromethane, and your second product are the 2 other atoms. the HCl. Alkane substitution gives you two products. You only substitute one chlorine ion at a time, and notice that it requires, and you need to know this, the special condition of high energy light, UV light. This will not occur in the room conditions. The description says one hydrogen is removed at a time from a hydrocarbon that's saturated, an alkane, and it's replaced with another atom. This is a slow, difficult reaction requiring ultraviolet light, and you get two products. You do not have to know the mechanisms this year. We are taking that off of the agenda for this year of COVID. Here's an example of alkane substitution. Notice that here you're starting with methane and ethane, two alkanes. You can use any of the halogens, but I point out that you only put one atom on, and you have a second product that's generated at the end of this alkane substitution. The next reaction is addition, and addition really says what it means, as opposed to substitution where you take something off and put something else on. Addition is where you only put atoms on. The reason you don't have to take anything off is because addition reactions require a double or a triple bond. You must have an alkene or an alkyne to undergo addition reactions. And so there are several specific addition reactions I would like you to know. You can always tell you've got an addition reaction because you've got this double bond or a triple bond. If you're going to be adding hydrogen, it's called hydrogenation. And I point out to you that hydrogenation is a commercial process that makes margarine from oils. If you happen to be adding, instead of H2, a halogen, you're adding like Br2 or Cl2, then it's called halogenation. You can add a hydrohalide, one of these, and both atoms go on. And importantly, look at this. You can add water, and that water would break to have the hydrogen go on and the OH would go on. Your end product is an alcohol. So it's important that you know with addition reactions, you get one product only, and you have both of the atoms of your second reagent going onto the molecule, adding across the double or triple bond and making a saturated compound. All right, the addition of water yields an alcohol. If you read the description, a reagent such as hydrogen or a halogen or water is added across the double bond. One product results. Double and triple bonds are very reactive. You don't need any special conditions. This reaction goes. And then it mentions the common additions again. All of these organic reactions, except combustion, are highly reversible. And I'd like to pause now and show you a demonstration of this process. I'm going to get bromine and add it across a double bond. This particular demonstration is a test for whether an organic compound has a double or a triple bond. It is a test called the decolorization of bromine, where if you lose your color of bromine, that means the molecule with which you have added it must have a double or triple bond. So this is a demonstration to show you how bromine, here is liquid bromine, can be used to test for the presence of a double or a triple bond. Bromine is a liquid that is orange in color It easily vaporizes because it has only London dispersion forces for an intermolecular force. Instead of using pure bromine, as I showed you, I am going to be using bromine water. Bromine water has bromine dissolved in a little bit of water. The reason it dissolves is because the molecule is so heavy. It has greater London dispersion forces. So this is bromine dissolved in water. Note the color. It's not as intense as pure bromine, but it is nonetheless intense. Here I have two different hydrocarbons. I have hexane, which is saturated. It has only single bonds. I have hexene. It has one double bond in it. You are going to see me put bromine water on the top of each of these chemicals in the test tube. So first I point out that the bromine water is not mixing with the hexane or the hexene, but I'm already losing my color here. I'm going to shake these two test tubes. This test tube that had all single bonds did not lose any of the orange. The orange is still there, which means the bromine is unreacted. But this test tube that had a an organic compound with a double bond, here the bromine orange has disappeared. It's called the decolorization of bromine. Because of this chemical reaction, the loss of color, I know that the organic compound that was in here had a double or triple bond. I know it was hexene, and now you can see there are two clear layers. The water and the hexene, now being 1,2-dibromohexane, still are not mixing. So that was a demonstration of this technique called the decolorization of bromine to test for an alkane versus an alkene. The next reaction is an addition polymerization. Addition polymerizations require you to learn 5 monomers and see how they build together into longer molecules. They are called addition polymerization because every one of these is going to have a double bond. The double bond will be broken, and all of the small units called monomers, like little Legos, will be hooked together to be one long chain of Legos. We represent the long chain of the bonded together monomers by putting parentheses around and putting N, saying N number, some big number of those small monomers have bonded together. So this reaction is saying that a certain number, let's say 100 million of these molecules came together and made a chain that was 100 million molecules long. 100 million individual molecules became one long molecule with 100 million subunits bonded together. There are 5 addition polymerizations you need to know, and these are on page 2 of your class notes. The description reads, double bonds in many monomers are broken repeatedly and joined together to form very long polymer made of repeating units. Several specific types you need to know. Note, only unsaturated hydrocarbons, that means a hydrocarbon with a double or triple bond, and we'll talk about only double bonds, undergo addition reactions. Saturated hydrocarbons do not undergo any addition reaction. So on page 2 in your class packet, you'll have to study this and practice it. You can stop this and fill it in. This is also the answer provided in Schoology, so you can look closer at your Schoology answer sheets. But the monomers for these 5 types of polymerization reactions are listed here. They're called ethene, styrene, propene, vinyl chloride, and tetrafluoroethene. You need to be able to write these 5 monomers. When they bond together, notice that the double bond disappears because you've broken it to be able to connect all of the monomers together. And those 5 polymers are polyethylene, polystyrene, polypropylene, PVC, and Teflon. You can read about their uses, but these are 5 reactions you need to recognize both with words and to be able to write chemically. Here I have these written for you again. The name of the polymer after the monomers are joined together. This is how you write the monomer. This is how you write the polymer once all the monomer units are hooked together. You need to know these 3 categories for those 5 polymerization reactions. You do not need to know conditions. Oxidation of alcohols is a reaction that we're going to be talking about today. The oxidation of alcohols is important. It is a redox reaction, and we know redox. In a redox reaction where you have oxidation and reduction, there is a transfer of electrons. You can tell it's a redox reaction because oxidation numbers change. What's important here is that primary alcohols undergo a particular kind of oxidation to become aldehydes and can further be oxidized to become carboxylic acids. This process of taking a primary alcohol through to 2 different possible products depends upon the technique you use, which I'll show you, whether you reflux or distill. Secondary alcohols only form ketones. Tertiary alcohols do not undergo oxidation at all. This is why you needed to be able to distinguish primary, secondary, and tertiary alcohols on site. So quickly, what I'm going to show you is a primary alcohol can undergo oxidation. That means you need to have an oxidizing agent that is reduced. That oxidizing agent is oftentimes potassium dichromate, and the chromium in potassium dichromate is Cr+6. When that dichromate undergoes reduction because it's an oxidizing agent, it becomes chromium +3. Do you see how the oxidation number of the chromium changes? What we remember about transition metals is that when the oxidation number changes, the color changes. So you can have a primary alcohol react with this oxidizing agent of potassium dichromate to form an aldehyde, and it can keep undergoing oxidation and become a carboxylic acid. I have demonstrated here that a secondary alcohol still to undergo oxidation needs an oxidizing agent, which is the potassium dichromate. You have the color change being an evidence of the reaction occurring, and you would get a ketone. Tertiary alcohols do not undergo oxidation. Please read carefully the description for your best understanding. This change in color of orange to green is the sign of an oxidation of an alcohol. So you can use it to distinguish a primary or secondary alcohol from a tertiary alcohol. Now, I am going to remind you that when oxidation numbers change, the color of the compound changes. Remember, the transition element of copper can have a copper +2 or a copper +1 charge. Those 2 copper oxides are 2 different colors. Likewise, here I am showing you, this is the color of potassium dichromate. Do you see how orange it is? When potassium dichromate is used in this oxidation of alcohols reaction, it has the chromium as the +6 oxidation state. It chemically changes to the chromium with a +3 oxidation state. So remember this orange color of the potassium dichromate going to the green color of the chromium +3 is the sign of the oxidation of an alcohol taking place. On page 3 in your class packet, I have an illustration to show you the difference between distillation and refluxing. When you distill a primary alcohol with the oxidizing agent in this reaction chamber, this is where the reaction is taking place. When you put a primary alcohol and potassium dichromate with a little bit of acid catalyst and you heat, that reaction produces the first product, which is an aldehyde. If you allow that aldehyde to go into the gaseous state and travel down this distillation tube, you can isolate the aldehyde in this test tube. That's because distillation allows you to separate off the first product that's made and isolate the aldehyde over here. You would see this flask go from orange to green, and with the distillation process, you would be collecting an aldehyde. However, refluxing doesn't let the product be isolated. Refluxing means you heat it over and over and over and over again. For a reflux, you would put the primary alcohol and the oxidizing agent, potassium dichromate, in this reaction chamber and heat it. When the first product is generated, it goes up the tube, but it falls back down. You keep all your chemicals reacting and being heated in this reflux container. Refluxing forces the primary alcohol to go first to an aldehyde, but keep undergoing oxidation to become a carboxylic acid. That's called complete oxidation of a primary alcohol. So there's a two-step process. You can stop after the first step and oxidize a primary alcohol to just an aldehyde if you distill. However, you can do both steps of the two-step process and take a primary alcohol and oxidize it through its aldehyde into a carboxylic acid if you use the process of refluxing. Please know this distinction. If you're using a secondary alcohol, you don't get an aldehyde or an acid. The process would generate a ketone. This oxidation of carbon compounds is a process that takes place in our cells all the time. If you look, we use carbon compounds as fuel for our body. If you would look at the oxidation number of these carbon compounds, you would know that we eat carbon compounds. And those carbon compounds have oxidation numbers. If oxygen is a +1, can you tell me what the oxidation number is for the carbon? It would be +4. Let's go up to the carbon monoxide. If the oxygen is a -2, I should do that in the same color. If the oxygen is a -2, the carbon will be a +2. In carbon dioxide, if the oxygen has an oxidation number of -2, the carbon will be, I'm doing the wrong color, a +4. So forget about the colors. What we have seen is a change in oxidation number here from a +4 to a +2 to a +4, and you would see that oxidation number gradually change through this oxidation ladder. Well, this is in your cells called the electron transport system. The electron transport system. And we use it to store energy of a very slow chemical reaction occurring in your cells. If you start with a carbon compound like alcohol that has a high oxidation number for the carbon, you can have that alcohol undergo several chemical reactions by undergoing oxidation in your body to ultimately exhaling carbon dioxide that generates and stores the energy in our body. This is the end of the video for Wednesday, May 5th. I'd like to remind you that we have looked at the first five organic reactions on this card. I hope that you will read the book and practice the material in your class packet and homework packet. You need to be familiar with these reactions, and you can only do that by trying to learn it and practice it afterwards. I will tell you that I'll email this link to all of you but I'll keep posting on Schoology the link to the video of the day and what the content of that video is. I thank you for your additional energy that you've invested in this video for Wednesday, May 5th on the first 5 organic reactions. I will now do the next video for tomorrow on the next 6 organic reactions. Thank you very much for all of your energy.